So we now get into quadratic functions, which is the main part of Chapter 2. So we've talked about quadratic functions a bit before, and we've said that a quadratic function is some function of the form y equals ax squared plus bx plus c, or we could also write this as f of x equals ax squared plus bx plus c. So it's a polynomial function with a degree of 2. The largest exponent is 2. X squared is our largest power of x. And so a, b, and c are just some real numbers, coefficients, and in particular, a is non-zero. Because if a was equal to 0, then this entire first term here would go away, and we'd be left with something that's linear. So b could be 0 and c could be 0, but that first leading term, the leading coefficient a, has to be non-zero. Alright, now we know that the graph of a quadratic function looks like a parabola. Those are our U-shaped graphs, or sometimes if they're flipped upside down, it's an N-shaped graph. And we say that the vertex of a parabola, the vertex of a quadratic function, is the point on the graph at which the parabola changes from increasing to decreasing, or vice versa. So in this first graph, we can identify the vertex of the parabola right here, because that's where the graph changes from increasing to decreasing. And here the vertex is this spot right here, where it changes from decreasing to increasing. Alright, now notice that some of these are U-shaped and some of them are more N-shaped, they're upside down. Notice that this has to do with the leading coefficient. In other words, the coefficient on the x squared term. In the first example, we start with a negative x squared, and we have an N-shaped graph. And in the second graph, we have a positive x squared, and it's a U-shaped graph. So this is really going to tell you exactly the shape of your graph. If your leading coefficient is positive, if a is positive, then the vertex, then it's going to be a U-shaped graph, and the vertex is going to be the lowest point on the parabola. In other words, it's the minimum point on your graph. When a is negative, when your leading coefficient is negative, like in our first graph, it's more of an N-shaped graph, and so the vertex ends up being the highest point, or the maximum point, on the parabola. This can be really useful to know when we're trying to get a sketch of what these functions look like, or what the graphs of these functions look like. Now, we can find the vertex of any parabola given just the equation for that parabola. So given a function of the form f of x is equal to ax squared plus bx plus c, we can find the vertex using the following formula. Negative b over 2a is the x value of the vertex, and then f of negative b over 2a is the y value. So just give you an example of what that looks like. If we wanted to find the vertex of the function f of x is equal to negative x squared plus 6x minus 5, well, first let's pick out our a, our b, and our c. So a is the coefficient on x squared. That's going to be negative 1 for us, just because we see a negative x squared there. B is the coefficient on the x term, that's a 6. And c is the constant, that's negative 5. We don't actually end up using c when we're trying to find the vertex, but that, it'll come in handy when we're trying to actually find the output. Alright, so if we want to find the x-coordinate of the vertex, we just need to use that formula negative b over 2a. So that's going to be the opposite of 6 over 2 times negative 1. In other words, it's negative 6 over negative 2, and this simplifies to just positive 3. And so our vertex is going to have an x-coordinate of 3. What's the y-coordinate going to be? Well, just take that x-coordinate and plug it back into your function. In other words, find f of 3, and that'll be the y-coordinate. So using this function up here, f of 3 is equal to negative 3 squared plus 6 times 3 minus 5, which is equal to negative 9. The negative's on the outside, so we square it first and then multiply by negative 1, plus 18 minus 5. That's 9 minus 5, which is 4. Okay. So the vertex is going to be at 3, 4. Okay, and it also asks us, is that vertex a maximum or is it a minimum? Well, remember, to figure out if it's a maximum or a minimum, we just look for the sign of the leading coefficient. In other words, look at the x squared term. If it's negative, your graph is going to be n-shaped rather than u-shaped, which means that that vertex is going to be a maximum. It's going to be at the top of a hill rather than at the bottom of a valley. All right, now what else do we have? To help us in graphing this, we know how to find the x and the y-intercepts of a graph. So we're going to do that here, and that'll help us get a better sense of where this graph is situated in the coordinate plane. Right, so remember, to find the x-intercepts, you set f of x equal to 0 and solve for x. So in my original equation up here, I've written all over it so it's hard to see. In my original equation up here, I'm going to replace f of x with 0 and solve for x. We have negative x squared plus 6x minus 5. I'm going to multiply both sides of the equation by negative 1 just so that I have a positive x squared term. It's easier for me to factor that way. So if I multiply 0 by negative 1, I get 0. And if I multiply everything on the right by negative 1, I get x squared minus 6x plus 5. Okay, this is just a little bit easier for me to factor. I need two terms that multiply to positive 5 and add up to negative 6. The only ones that would work would be negative 5 and negative 1. Alright, so setting each one of those equal to 0 gives me an x-intercept at x equals 5 and at x equals 1. Okay, so that's going to help us in graphing as well now that we know that we have x-intercepts at 5, 0, and 1, 0. And finally, to find the y-intercept, this is the easier one to do. All we have to do is evaluate the function at x equals 0. In other words, evaluate f of 0. That's going to give me negative 0 squared plus 6 times 0 minus 5. Alright, that's just negative 5. In other words, this ends up just being whatever your c term is. Okay, so the y-intercept would be at 0, negative 5. Alright, so now we have a vertex of the graph. That's at 3, 4. We have two x-intercepts and we have a y-intercept. Using all that information, I'm able to sketch the entire graph down here. So I'm going to plot those important points. Let's start with the vertex at 3, 4. 3, 4 is up here. Then I'm going to plot my x-intercepts at 1, 0, and 5, 0. And finally plot my y-intercept at negative 5, 0, negative 5. And I know that the shape of the graph is sort of n-shaped. We had said that before, which means I can fill this in and I get a graph that looks something like this. Alright. So knowing the vertex of your graph and the x and y intercepts of your graph is often enough to sketch the graph of a quadratic equation. Except it's not always so simple to find the x-intercepts, right? The y-intercepts you can always find, but the x-intercepts can be tricky if they don't factor like they did here, right? So what do we do if your quadratic equation doesn't factor nicely and you're trying to find the x-intercept, you're trying to find the zeros of that function? Well, luckily in that case we have the quadratic formula to help us. So the quadratic formula will always help you to find the x-intercepts or the zeros of a function, provided that there are any. All right, and the quadratic formula says if you want to find the zeros of a quadratic function of the form ax squared plus bx plus c, you use this formula right here. Negative b plus or minus the square root of b squared minus 4ac all over 2a. It is a lot, right? It's pretty messy. The numbers don't always turn out nice, but it always works, right? And factoring doesn't always work. So it's good to have this memorized so that you can use it whenever you need to, whenever you can't factor. So let's try this one here. Find the zeros of the equation y equals 3x squared minus 8x plus 2, right? Remember, the zeros is just another way of saying the x-intercept, or the x-coordinates of the x-intercept. And so essentially what we'd be doing is replacing y with 0 and solving for x. But here's the problem. I don't know how this factors. I don't know if it factors nicely. I'm not very good at factoring when you have a coefficient, a leading coefficient other than 1. You can try, see if it works, but I know that the quadratic formula always works. So the first thing I'm going to do is pull out my a, my b, and my c. A is the coefficient on x squared, so that's going to be 3. B is the coefficient on x, so that's negative 8. And c is the constant term, so that's 2. Now I'm going to fill all this information into the quadratic formula. Replace a with 3, b with negative 8, and c with 2. And I'll get the following solution. X is going to be equal to negative b, so the opposite of negative 8. Right, there's a negative to begin with in the equation, and now there's a negative here. Plus or minus the square root of b squared, that's negative 8 squared, minus 4 times a, which is 3, times c, which is 2. All of that's going to be divided by 2 times a, so 2 times 3. Alright, well I'm running out of space here. Let's see what I can do. I can simplify this further. The opposite of negative 8 would be positive 8, plus or minus the square root of 8 squared is 64, well negative 8 squared is 64, minus 4 times 3 times 2 would be 24, all divided by 2 times 3, which is 6. Okay, can I simplify this any further? Sure. We'd have 8 plus or minus the square root of 64 minus 24. That's going to be the square root of 40 divided by 6. Ooh, okay. So I'd be okay with this as a final answer, 8 plus or minus the square root of 40 over 6. It is technically possible to simplify this a little bit further. If you know some tricks for simplifying radicals, for example, you could write this as 8 plus or minus the square root of 4 times the square root of 10. Right, you can break this up as square root of 4 times square root of 10 because 4 times 10 is 40 divided by 6. And then you can simplify that square root of 4 to be, square root of 4 is just 2 times the square root of 10 over 6. And then you could even factor out a 2 and cancel it if you wanted to. Right, but I'm okay with leaving it just like this. And just so that we're clear on what this means is, erase this here, we have two solutions. This expression with a plus sign between the 8 and the square root of 40, and the same expression with the minus sign. So our two solutions, our zeros, or our x-intercepts, are going to be the number 8 plus the square root of 40 over 6, and 8 minus the square root of 40 over 6. Chances are you probably couldn't have guessed that these are the solutions by factoring, right? It's messy, and so you can see why you might really need to use the quadratic equation sometimes. Let's do another example. We're going to find the x-intercept, that's the same as saying find the zeros, of the quadratic equation y equals negative 9x squared plus 6x minus 1. Again, if you'd like to try to use factoring, you can see if it's possible to factor, but I'm just going to set this equal to 0 and use the quadratic formula. Right, this is what we're doing. We're setting this equation equal to 0, negative 9x squared plus 6x minus 1. So the first thing that I'm going to want to do is pick out my a, my b, and my c. A is the coefficient of x squared, so a is negative 9. B is the coefficient of x, so that's 6. And c is the coefficient of, nothing. C is the constant, that's negative 1. So the quadratic formula tells us that x should be equal to, right, remember from the last page, it's negative b, whoops, so don't do that. Let's try it again. Negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So when we fill that in, we get negative 6, right, because b is equal to 6, plus or minus the square root of 6 squared minus 4 times negative 9 times negative 1, all divided by 2 times a, so 2 times negative 9. Alright, so let's try to simplify this some more. In the numerator we have negative 6 plus or minus the square root of 6 squared is 36, minus, we've got a negative 9 times a negative 1, so make those positive. We still have a negative on the outside, so negative 4 times 9 times 1 would be negative 36, all divided by 2 times negative 9. That's negative 18. So what do we get here? Well, on top we have negative 6 plus or minus 0, because 36 minus 36 is 0, and the square root of 0 is 0, all divided by negative 18. This just simplifies to negative 6 over negative 18, or the negatives cancel out and we can reduce to 1/3. Okay, now in this case we just had one solution. In our last example we had two different solutions. And did I lose an example along the way? Nope, I didn't. Okay. Notice that the reason that we had one solution here as opposed to two different solutions is because when we simplified the stuff that was underneath the square root sign, we got a 0. And the square root of 0 is just 0. So that plus or minus meant that we didn't actually get two different solutions there, because negative 6 plus 0, negative 6 minus 0, it's the same expression, right? They're equivalent to each other. So anytime that stuff underneath the radical sign, that b squared minus 4ac, anytime that's equal to 0, you're only going to end up with one solution, right? If the discriminant, this is what we call that, so b squared minus 4ac is called the discriminant of a quadratic equation. If the discriminant is 0, then we get that x is equal to negative b plus or minus the square root of 0 over 2a. That is, we get negative b over 2a. Haha, that might look familiar. That's the vertex. Because that plus or minus is both a 0 and it goes away, we only get one solution. That solution ends up being where the vertex is. If the discriminant is positive, that's what we had in the last example. Try to go back a page. Right, the discriminant, the b squared minus 4ac, in this case was 40. Right, when we simplified b squared minus 4ac, we got positive 40. In that case, because we got a positive number under there, it had two solutions. Now finally, what if the discriminant was negative? What if you had, use a different color here. What if you plugged everything in and you got negative b plus or minus the square root of something negative all over 2a? This was a negative number underneath the square root sign. Well, remember, a square root of a negative is undefined. It's not a real number, and so in this case you don't get any solutions at all. This is a nice shortcut for trying to graph something, because you can find the discriminant pretty easily and determine whether there's any zeros or not. If that discriminant's negative, you know right away that there's no zeros, there's no x-intercepts. If the discriminant is positive, you know that it's going to cross the x-axis twice. Just to give you an idea of what this looks like in a graph. Let's see. If the discriminant is positive, then you have two x-intercepts, maybe here and here. So your graph would look like this, or maybe it would be upside down. In the second case, if your discriminant is negative, then you don't have any x-intercepts. You don't have any solutions here, which means your graph is going to look maybe something like this. Right? It doesn't cross the x-axis at all, or maybe something like this if it doesn't cross the x-axis at all. And if the discriminant is 0, that means you have exactly one x-intercept, right? 1, 0. And so that means you only touch the x-axis in one single spot. So maybe your graph looks something like this. That one single spot where it touches the x-axis, that's got to be the vertex of your parabola, which is exactly why we get this formula of negative b over 2a, right? That vertex formula that we saw before. Okay, the last thing that I want to mention is that if you're trying to find the zeros of a function, if it's possible to factor, it's usually the easiest way. So before you jump into using the quadratic formula, which can be really messy and easy to make little arithmetic mistakes, it's a better idea to see if it's possible to factor. So let's look at one example of that. Consider the function f of x equal to x cubed plus 9x squared minus 10x. We want to find the zeros of this, right? So we set f of x equal to 0 and solve for x if possible. All right. Notice I can't even use the quadratic formula yet because this isn't a quadratic equation. It's a cubic equation. The largest exponent is x cubed, not x squared. But the first thing you should think when you see something like this is, what can I factor? Can I factor at all? And you notice, hopefully, that every term has a factor of x in it. So the first thing that I would want to do is factor out an x. In other words, use a distributive property here. Take an x out, divide each one of these terms by x. So x cubed divided by x is an x squared, plus, this is x squared, plus 9x squared over x would be 9x, and 10x divided by x would be just 10. So when I factor out an x, I have an x on the outside, and inside the parentheses I have a quadratic. So I could try to find the zeros of what's inside the parentheses using the quadratic formula, but again, if you can factor, you should factor. So I'm going to try to factor this first. So inside the parentheses I have this quadratic, so I'm looking for two numbers that multiply to negative 10 and add up to positive 9. 10 and 1 should work, right? I'll do x plus 10, x minus 1, right? Those numbers multiply to negative 10 and add up to 9. So this is factorable. Now it's as simple as just taking each one of these factors, the x on the outside, x plus 10, and x minus 1, and setting each of these factors equal to 0, and solving. Well, the first one, there's nothing to solve. We had a factor of x on the outside, so if x equals 0, then this entire expression will be equal to 0, so the equation will be true. If x plus 10 were equal to 0, in other words, if x was equal to negative 10, then that expression would be 0, and the whole thing would be 0. And if x is equal to 1. So, this function, this cubic function here, has 3 zeros. It crosses the x-axis in 3 places, namely at x equals 0, at x equals negative 10, and at x equals 1. We can see that if we try to sketch that, we have an x-intercept at 0, at negative 10, and then at 1. So if I had to guess at what this graph looks like, knowing what I know about cubic functions, it's probably going to be something like this. Okay, so finding these x-intercepts can be really useful in sketching a graph. Just make sure that you go through the proper steps. See if it's factorable first, and if it's not factorable, then use the quadratic equation or the quadratic formula wherever it's appropriate.